Welcome to the Explainer. Today, we're diving straight into a really critical question. What actually happens when an AI system repeatedly trains and improves itself, but without the proper constraints? We hear a ton about AI getting smarter and faster, but what happens when it learns its own mistakes in a continuous, endless loop? Well, as we're going to see, a small error becomes incredibly dangerous when an AI teaches that exact same error to the next version of itself. So, to really understand this, we're going to walk through our 6 main topics. 1. The self-improvement promise. 2. Anatomy of recursive drift. 3. 3 forms of drift. 4. Agreement is not verification. 5. The energetic paradigm. And finally, 6. Achieving recursive stability. Let's jump in. Section 1. The self-improvement promise. The circular loop of AI advancement. Okay, so on paper, this 6-stage cycle looks completely straightforward, right? The system diagnoses a weakness, generates some training data, trains or modifies the model, evaluates the result, approves the change, and then, boom, begins the next cycle. But there's a huge hidden danger lurking right here in this loop. What if the model's judgment is even just slightly off? Section 2. Anatomy of recursive drift. How subtle biases accumulate. Think about what happens if an evaluator rewards an imperfect shortcut. The system actually learns that the mistake is correct. So step by step, it mutates a small distortion into an accepted shortcut, which becomes a training signal, which then establishes a brand new evaluation standard, ultimately creating a self-reproducing error. Imagine a model passes a benchmark, but totally ignores a critical edge case. Well, next cycle, it uses that false success to generate more data. It hasn't just repeated a mistake, it's literally learned that the mistake is the goal. And this hits the nail on the head right here. A normal error affects one output, but a recursive error affects future outputs. A normal error just ruins a single, isolated result. No big deal. But in a recursive system, those current distorted beliefs shape the entire next generation, which makes it incredibly difficult to ever return to a correct state. Section 3. 3 forms of drift. Evaluator, data, and objective. So how does this actually play out? Well, the first way is evaluator drift. This happens when the judge starts rewarding the wrong behavior. For example, an AI writes software that easily passes a benchmark test, but completely fails in reality because it ignores edge cases. Because the system is acting as both the generator and the judge, its standards deteriorate. The benchmark score might keep going up, but the actual software quality plummets. The second form is data drift. We see this a lot in scientific discovery models. Basically, the system generates training examples based on its own mistaken assumptions. A slightly biased early hypothesis causes the system to narrow its search, finding only evidence that confirms that unverified assumption. So it interprets a result with a slight bias, uses that to generate the next hypothesis, and eventually becomes highly confident in a research direction that was fundamentally flawed from the start. And the third is objective drift. This is where a complex, multidimensional goal, like, say, creating a safe and cheap material, gets dangerously narrowed down to optimizing just an easier measurable proxy, like maximizing strength. The system figures out, hey, it's way easier to optimize this proxy than the actual broad goal. It might invent a super strong material, sure, but completely sacrifice cost and toxicity in the process. The measured proxy looks fantastic, but the real-world result is an absolute disaster. Section 4. Agreement is not verification. The trap of redundant failure modes. Okay, I really want you to pay attention to this warning. Agreement is not verification. It is so tempting to think that just having multiple AI agents checking each other's work ensures accuracy. But listen, if 10 identical agents share the exact same base model, data, benchmark, and reward structure, they're all going to reach the exact same flawed conclusion. They're just sharing redundant failure modes. They aren't creating independence. They're literally just creating repeated, blind confidence. Genuine, independent verification demands true diversity. You absolutely need tests, external evidence, alternative models, simulations, human review, and actual falsification attempts. You need evidence and predictions that are designed to actively falsify the hypothesis, not just rubber stamp it. Because the more powerful that recursive process gets, the more absolutely vital these truly independent verification channels become. Section 5, the energetic paradigm, balancing generation and correction. This brings us to a pretty fascinating concept. Recursive stability exists only when corrective capacity removes damaging variation faster than the system reproduces it. It's a balancing act, pure and simple. No complex system is perfectly error-free, right? That's impossible. The real issue is whether that error is allowed to reproduce. If your mechanisms scrub away damaging variation faster than it multiplies, your system remains stable. But if error generation outpaces correction, you drift. Section 6. Achieving recursive stability. Building architecture for reversible evolution. Let's compare this visually. On the unstable side, you've got shared biases, single benchmarks, lost history, and errors permanently stuck in memory. The error reproduces way faster than correction. But on the stable side, you have independent verification, multiple objectives, traceable changes, checkpoints, and rollback capacity. Effective recursive improvement absolutely requires reversible evolution. If a capability deteriorates, you must have the architecture in place to simply roll the system back to a safer checkpoint. A trustworthy system has to act like a diligent historian. To preserve that history, it needs to constantly record what changed, why did it change, which evidence justified it, which evaluator actually approved it, which constraints were tested, and which capabilities deteriorated. Without capturing this exact history, a future version of the system might observe a drop in performance, but it won't have a clue why or where the drift began. And let's be real, speed without stability is just accelerating without knowing your direction. I want to leave you with this final, incredibly powerful thought. The goal is not zero error. The goal is to prevent error from becoming structure. We are never going to eliminate every single mistake, but true recursive stability ensures that those inevitable errors are caught way before they become the foundation for the future. So as we rely more and more on these self-improving systems, we have to ask ourselves, are we merely building machines that improve their speed, or are we building architectures capable of remembering how to correct their own course?